Hello, hello. Let me know if you guys can hear me. It was having some trouble connecting, but it seems like I'm live now. So, how are you all today? I'm going to talk about how to make this specific design. As you can see, I don't have the skill to like make an eyeball, but I started with a picture of an eyeball, and if you can zoom in, it's been tessellated in an interesting way. And also, you can see that there's some like elements of detail going on here with the lines that are touching each other. So you can see that over here as I zoom in. Also, there's a small chance my computer might crash as I do this. But as you can see, there's a significant amount of detail here, and I want to discuss how I did this. So I hope you guys are all excited. All right. Let's get started. I'm just gonna remove this for now, just because it takes a lot of RAM to keep that particular image up. Well, whatever, I'll keep it up. It looks nice. Just generate it again. Okay, so there it is again. And yeah, I'm just gonna talk about how I did this, stuff like it, what's going on here. And so first and foremost, there's the question of inspiration. So I do want to mention the like piece that I was inspired by, and it's actually a sculpture. It's by an artist by the name of Charles Perry, and it's called the Icosa Spiral, or Icosa Spiral with an E at the end. I'm not sure how to say it. And so this is a sculpture. Apparently it sits in San Francisco. Those are pursuit curves, absolutely. So I don't know. I saw this, and I really, really liked this particular sculpture. Let's see if we can zoom in at all here. Well, I don't know. Maybe. I do not know. Anyways, as Petros Paulus has already figured out, I mean, I looked at this, and clearly there are pursuit curves going on in this sculpture. And so what is a pursuit curve would be like the first question here. And so a pursuit curve, first and foremost, is, the idea is very, very simple. So you take a, let's see, so you take something that you're interested in, you take like a bunch of points, or you take a point and another set of points. And the idea is that, let's say this point is the pursuer and this one is the pursuee, so this one's running around. And this one is chasing after it, So this one is being pursued, and this one is the one chasing after it. So you'll notice that this one might have some motion independently, right? And the idea is that this point is always traveling in the direction of the other point. So for example, if you draw a line between these 2 points, the tangent here will always be pointing in this direction over here. Also, I think the music's just slightly too loud. Okay, so essentially, like the tangent here will always be pointing in this direction. And so that gives rise to a pretty simple differential equation. I mean, you can just type in pursuit curves. And in one dimension, you get a pretty simple differential equation. It's here, I'll put it up. It's like LT, so L is the equation of the thing being pursued, and F is the equation of the thing that's pursuing it. And so you immediately get that LT is going to equal FT plus X F prime of T. Pretty simple over here. And so all this equation is saying is that the thing that's being pursued, there's some point on the tangent line of the equation of F that is exactly the position of the thing that's being pursued over here. So I just wanted to mention this, and there's all sorts of differential equations you can do. You can solve, you can make interesting pictures over here in 1 dimension or higher dimensions. It's up to you. But the neat thing is you actually don't need to solve this differential equation to draw interesting pictures, because you can do neat little numerical approximations, fundamentally, of this differential equation. And so one classic thing that people do, or at least love to do, is they'll start with 4 points on a square, for example. So, they'll just take a square, and you'll have 4 points, right? You can imagine the 4 points are the 4 corners of the square. So Let me draw 4 points basically on the 4 corners of the square. And you just have them pursue each other. So this one is chasing after, so this point is chasing after this point is chasing after this point is chasing after this point, and this point is chasing after this point. And once again, you don't, you'll get logarithmic spirals if you actually bother to solve this differential equation, but you don't actually have to solve it. You can just do a numerical approximation. So you can just do like a step in time, and in one step in time, so this point will move to, for example, this point over here, and this point will have moved to this point over here, this point will have moved to this point over here, and this point will have moved to this point over here. And then the thing that you do is you just draw the polygon made by the 4 next points. So, you just draw the polygon. I have a computer simulation too, so don't worry about my ugly drawings. You'll see pretty ones soon enough. So, do that, and then you just do it again. You do another step, and so by that point, this point will have moved here, this point will have moved here, this point will have moved here, and this point will have moved here. And you essentially do this by a percentage every time. So like maybe every time the point travels like 10% of the way to the other point, and then again you draw the polygon. So you just move over here, this one over here, this one over here, this one over here. You just keep doing this over and over again, and you get this like neat little pursuit curve diagram, which is extremely popular. You see it all the time. And so it's actually really, really easy to do in code. So let's see. Let's do a pursuit curve for a square, and let's do 30 iterations. And so random color here. Well, that's not a square. I forgot to write 2 pi over n here. Okay, there you go. So that's a square in a random color. A little bit of a faint color. I can roll again, get a better color. There you go. So this is a square, and you can see kind of the pursuit curves going on here. It's a really simple idea, honestly. Like it's, I remember a puzzle like this. The question is, in the square case, how far does each point travel? Yeah. If you actually bother to solve the differential equation, you'll just get logarithmic spirals, which you can integrate. Fairly easy to figure out, how far each point travels. But today, I'm a little light on the math. I just wanted to try and see if I could make a pretty picture out of this. So that was the idea fundamentally. And you can, it's really not hard, and you can set up your code where you do as many iterations as you like. So for example, if I do 100 iterations over here, you'll spiral further and further inward. And I believe in the 70s this was a very popular thing to do amongst artists, because it gives this kind of beautiful illusion of depth, right? Which is really nice. And of course, you don't have to do this with points in a regular polygon fundamentally. You can do this with like random points. So let me try it with random points. So instead of let's see. I'm just going to comment this out, and I'm going to throw in random points, and we'll just see what happens. So instead, I'm going to take the same code and do n random points. I believe the code that I want is, instead of a table, I think I can just ask this to do random real from, let's say, -1 to 1, and give me a, I don't know, 5, maybe 10. Well, let's start with a 5. Like, give me a 5 by 2 array. And hopefully it doesn't yell at me. Okay, so you look at that. Maybe let's start with a 3 by 2 array. Okay, so I get this like wonky triangle. Sadly, this is not giving me a figure that. But in the square case, it's easy. It's just the square side length. That's actually really interesting, Ken. I never actually bothered to solve the problem. You really get just the square side length, huh? I didn't know that. That's actually really neat. Maybe that's worth. Yeah, I might do that in my spare time, because that's really cool, actually. Yeah, so you can roll over and over again. I'm kind of curious what happens if I do like a bunch of points, like 10 points. Ooh, that looks really cool, actually. So I just generated 10 random points and have them all basically pursue each other, and you actually get really neat patterns when you do this. So Yeah, I think that's pretty cool. I might just do this again because I'm having a good time. Let's do 20 points. Wow. Wasn't expecting this at all. Huh. It's quite neat. I mean, I'm having a little bit of trouble, honestly, interpreting what's going on here. I think part of the issue is that I'm asking. Oh yeah, I think part of what's going on with these patterns is that I've essentially, the way that I coded this is I asked it to color each of these polygons. So for example, you know, I ask it to put a color in here, a color in here, a color in here. But if you have a non-convex polygon, essentially most pieces of software that color it will do it like a checkerboard coloring type situation. So for example, the color will go in here and here and here, which is why I think you're seeing the like weird white patches in the middle. It's just basically where the polygon is folding over itself. Okay, but in any case, those are pursuit curves, right? And so what this artist Charles Perry has done is he combined the idea of a pursuit curve with an idea of an icosahedron, which is a lovely idea. I can imagine this oriented in 3D space. That's true, actually. I mean, I didn't write the code to deal with 3D space, though it wouldn't be. I mean, you could do this in any dimension, honestly, and it would be really cool, I think. Actually, you know, it's ill-advised to do stuff to like code on stream, but I'm gonna try it. So I think what I'm gonna do, let's just see what happens. I'm going to do a 3D version of this right now, because why not? So let's try it. So I need to do graphics 3D, and then maybe let's make it smaller, just so it's a little bit easier on my computer, which is also streaming right now. So okay, I don't know what's gonna happen. That's cool. Okay, so it's this is kind of like folding in on itself because yeah, it's drawing polygons in 3D, and you know, sometimes there's like moments of self-intersection with these polygons fundamentally. It doesn't look too bad. Let's try like 50 points. It's probably a bad idea. Okay, just making a bit of a wild and crazy mess over here. I should probably stop doing this and get back to actually doing math. I don't know. I just haven't made something in a while, and it's really fun to just kind of like mess around with stuff and see what happens. Honestly, this does look really cool. You can kind of see through it at places. Wow. Yeah, and that's just like 50 random points in R3. And I just drew, and like they're all chasing after each other, and apparently this is what you get. Okay. Pause. Let's regroup and talk about the next idea here. So what I really wanted to do was combine, and this is where most of the mathematical content of this stream is going to be. Hold on. My video seems to be frozen. Okay, I'm just going to turn off my camera and turn it on again. Okay. Just, okay. Hold on. Just need to add. This is embarrassing. I don't know why the video died. See here. Okay, I don't know why the video died. I have like an emergency webcam as well that I can use, so I might just use that. Okay, so this is my. So I'm on a webcam now. Yeah, it looks about the same. So. Let's see. Okay, back to business. So, what am I? Hold on, let me adjust this a little bit. Okay. All right. So what we have here is a bunch of weirdness. These are 50 points in R3 that are essentially chasing after each other, which is cool. But the actual honest like math content of this was that I really wanted to combine this idea of pursuit curves with a tessellation. Okay, so what's a tessellation? A tessellation is essentially when you take the plane or maybe some kind of rectangle and you divide it into polygons, right? And some tessellations are going to be periodic, some are going to be not so periodic, and so you just kind of like divvy things up into polygons in some way. If you divide it up into triangles, it's called a triangulation, and so on. And of course, there's all sorts of crazy, beautiful tessellations out there in the world that you can look at. Some of them have amazing kind of periodicity, and you can see lots of beautiful patterns coming through. And actually, I think there's a mosque where you can see. So there's a whole theory of tessellations and tilings, and I think there's a mosque. I can't remember the name of it, but in this mosque you can apparently see all possible tilings by some description of tilings. So like you can see all of so there's 17 what are called wallpaper groups, which encapsulate all the possible symmetries you can have when you tile the plane. And it turns out that there's a mosque. Let me actually. I don't want to be disrespectful. Let me look up the name of the mosque. So, tilings. How about that? Tessellation. Let's see here. Wallpaper groups. Yeah. The Alhambra Palace in Granada, Spain. Apparently you can see it has been claimed that all 17 of these groups are in the Alhambra Palace in Granada, Spain, though this is disputed, apparently. The variety and sophistication, I'm just reading this off of the Wikipedia page if you're curious. So the variety and sophistication of the Alhambra tilings have surprised modern researchers. So you can find a huge variety of these tilings if you're willing to visit various mosques and palaces all around the globe. You can see a wide variety of these. So my question was basically, I want to incorporate these kind of pursuit curves, these kind of spiraling patterns into, basically, tessellations of some kind to make pretty pictures. So the way that I wanted to do that was, well, first of all, it's kind of annoying and difficult to encode a wide variety of tilings, but there is one class of tilings that's both extremely useful and also really easy to encode. In fact, most computer algebra softwares will already have this encoded in some capacity. And so the type of tilings that I wanted to use are called Voronoi, tessellations. These are extremely useful. They come up literally all the time, regardless of the field that you are in. And so let me explain what a Voronoi tessellation is. So the idea is very simple. So let's say you have a rectangle, okay? So I'm just gonna, or any region in space, or even in 3D, you can do this in any dimension fundamentally, okay? And let's say you pick a bunch of points in this rectangle over here. So you're gonna pick a point here, a point here, a point here, a point here, maybe just like a bunch of different points. And the idea is that you divide this into regions based on which point is the closest point. So for example, for this point, you ask the question, which of all these red points is the closest to this green point? And the answer is going to be clearly this one. And then you can basically section off this entire figure into regions based on which of these points is the closest. So And you have this. So as you can see, you get a very kind of natural tiling over here, right? Based on sort of which of these points is the closest point. I'm obviously not going to be entirely accurate as I do this. Probably like over here. So, okay, I'm going to stop pretending like this is an accurate picture, but you get the idea. So you're dividing this region into pieces based on which of these points is the closest, okay? So a really neat way to think about these, so I made the claim earlier that these types of tilings come up in nature a lot, and it's exactly as Ken is saying. Right now. So one of the reasons these come up in nature a lot is that you can imagine there's some kind of like microbial growth or something happening at each point, and these boundary lines are where these are going to intersect each other. So there's actually like a nice animation of this on Wikipedia. I'm just going to show you. So let's see. Voronoi diagram, blah, blah, blah. Okay. So this is a lovely animation you can see. So you can imagine there's a sphere growing at every single point, and these spheres will eventually run into each other, right? And you can see the Voronoi tessellation or the Voronoi tiling being formed exactly as that happens. And so this is a really interesting idea. So as you can imagine immediately that this would come up in nature a lot, because there's a lot of situations where you have like a bunch of different points and there's like a growth of some kind, a growth of some phenomenon or some idea that's happening at each and every one of those points. And then eventually they'll grow and run into each other. So that's why you'll see patterns like this in nature all the time. So it comes up in the biological sciences. It also comes up like when you study geography and stuff like that. So for example, there's like a neat picture of like Britain being, well, I don't see it here, but another way that this comes up a lot is in computer science. There are these, so if you learn machine learning, there are these classification algorithms called k-nearest neighbors. The k-nearest neighbors algorithm. So basically you want to classify things based on what their nearest neighbor is, essentially. So the Voronoi tiling essentially shows you the one nearest neighbor diagram. So if you're interested in machine learning, they come up there as well. And actually, if you take an introductory machine learning class, one of the first things they might teach you is fast algorithms to implement this Voronoi tessellation. So now that you have a brief description from me, I actually wanted to show you some. And so I wrote this little like dynamic thing. And so for example, these are a bunch of randomly selected points in R2, and you can see how they divide up the region, how they tessellate the region. And you can experiment with it by moving around these points, and it does interesting things when you do that. I don't know, this is just fun to play around with. And you can see how the Voronoi tessellation changes based on what happens when you essentially move around points. It almost looks like soap bubbles, I think, because soap bubbles do have similar behavior, though I don't know if they have precisely the same behavior, but just like spheres that are kind of running into each other, and then you have these like boundary phenomenon that happen fundamentally. And so given an arbitrary tiling, you can essentially put these pursuit curves in the polygons of an arbitrary tiling, and that was the idea that I had fundamentally to make this. So for example, you can also do animations with this. So this is a weird one. This one didn't quite make the cut, but I found it to be a lot of fun to play around with. So if you take a random Voronoi tiling and another random one, you can kind of watch. Let me show you two examples of this. So you can interpolate between two random Voronoi tilings. So let me just do this. gonna delete this Voronoi mesh of 1 minus t p1 plus t p2. Okay, and you can kind of see one Voronoi mesh randomly like interpolating into another one, which is, I don't know, it's kind of fun to imagine and to look at. I can imagine there's some artistic application of this that I don't know about or haven't thought about yet, but I just think it makes for like really interesting pictures to just watch a random Voronoi mesh go into another one. And then of course, at first I thought that's what the video was going to be fundamentally, but I don't know, I just didn't feel like it was pretty enough. And then you can also insert all of the pursuit curves into this, and that makes for a really insane looking kind of picture here. Look at that. Yeah, that's super weird. In any case, this is about as much mileage as I was able to get out of a random kind of just like randomly throwing points on the plane and doing a Voronoi tiling and then filling it with pursuit curves. So after that, I decided I would be more regular in my pursuits. So for example, you can get a lot of kind of regular looking tilings of the plane using Voronoi embedding. So for example, if you think about what a regular hexagon is, right? So imagine tiling the plane with regular hexagons, like so. So this is me kind of tiling the plane with the regular hexagons. It's actually not too hard to see if you just stare at it for a little bit that this is going to be the Voronoi tessellation of points placed like so. You can imagine a point placed at the center of mass of each of these hexagons, and you'll get, you know, a perfectly good looking Voronoi tessellation over here. And then you of course realize that you know, these are all equilateral triangles, right? So for example, this is an equilateral triangle, that's an equilateral triangle. So you just need to do the Voronoi tiling of a grid where the distance between this point and this point on the x-axis, like these are all √3 apart, right? So this to here will be √3 apart, and here to here will be 1 apart. So if you just make a nice little grid where the distance between all of the x points is √3 and the distance between all the y points is 1, and then you do the Voronoi tessellation of that collection of points, you'll get precisely the hexagonal grid. So let me just show you that first. Just one. There you go. What a neat little, hold on, I'll make it a bit bigger. Okay, so it's just like a really, I don't think so. I don't think so. So for example, there are aperiodic tilings that exist in the world, and I have my doubts as to whether or not you could get an aperiodic tiling using a Voronoi tessellation. But you know what? Actually, it's not a bad question. I don't actually know the answer to it. So I feel like I guess I'm just giving you my guess. My guess is that it's not true that all convex polygonal tilings compatible with Voronoi, but I can't think of an example right now. So yeah, so okay, let me think. Let me actually like think about this for a second. So let's see here. So there's like a tessellation out there that only uses pentagons that was only discovered in 2015. It's called the 15th monohedral pentagonal tiling. Yeah, this one. I don't know. I haven't checked, but I highly doubt that this particular tiling you could get with you know, by taking a bunch of points in the plane. But you know what? I haven't checked it. I mean, maybe by some miraculous coincidence. Yeah, actually, I don't see how this would be possible. My confidence has gone up from like 90 to 95% staring at this. that you could not get this. It was kind of a weird answer, but I hope you feel like your question has been somewhat answered. Lost Genta. So for example, the reason I'm super suspicious is because, for example, if you look right here where where like my finger is pointing, like it's like a line, and then there's another like orthogonal line over here, and I don't actually know how you could possibly get that using a Voronoi tiling. So I'm 95% sure that it's just not going to happen. Anyways, let's continue. So as you can see, but you know, I'm not saying you can get all of them, but you can get a lot of interesting ones, and that's basically the idea that I had. And of course, once you have these, you can draw neat little spiral pursuit curves in them. So here, let's draw 10. And ooh, like that's neat. You know, I feel like there's something fun going on here. You could tile your bathroom with those, I feel like, and you'd have like a pretty you'd have a pretty trippy setup over here. You know, I'd say that looks very nice. And you know, I wanted to generate something pretty, so I experimented with like random colors, random edge colors, but I wasn't 100% satisfied with this. And so I went from hexagonal tiling to like just using triangles. So to use triangles is actually like a little bit trickier. So let's think about what set of points, if you took their Voronoi diagram, would actually give you like a triangular tiling, like just a classic equilateral triangular tiling of the plane. So, you know, you have, I'm going to try and draw smaller triangles here. So have neat little hexagons here. And so, yeah, I'm just telling you guys how I experimented with these ideas. Feel free to experiment with them however you would like to experiment with these ideas. I do think they're a fair amount of fun. Okay, so this is, let's say, what we are interested in. And so you notice, for example, you would have to have a hexagon of points here, right? And here again, you would have to have a hexagon of points if you wanted to do the Voronoi situation. But you have a point kind of missing over here. So, for example, if I were to look at this collection of points, they actually look like the vertices of a hexagonal tiling. Like so. Right? So if you're after kind of a triangular tiling of the plane, then the point set that you wind up getting is the vertex set for the hexagonal tiling of the plane. And so the question is, how do you, kind of quickly write code to get this? Because, like I said, I didn't want to go through the trouble of making things, too complicated. So essentially what I did is, if you look at the missing point over here, let me draw all the points that are missing here. It's basically all of the points in the triangular tiling, but like every third point is missing essentially here. So all I did was I populated a table with a grid, but I told it to omit the points in the odd rows that were 0 mod 3 and the points that were in the even rows, but omit the points that were 1 mod 3, and then shift these by 1/2 forward. And so that's just a quick way to populate a grid like this so that you actually get kind of a triangular tiling of the plane. So let me show you what that looked like. So let's see here. Let's see. This is it. So you can kind of see like the outer edges of the Voronoi. Let's see. Let me make it smaller so you can only see kind of the part that matters here. Or did I already do it down here? No, this is a mess. This is I played around with this for a long time. So let's see. Plot range. Let's go 210. Okay, there you go. So that's I mean, I also don't think that Meridius. I stared at this for a long time. You're getting the distilled hour version of like my misery for many hours. So, but I hope what I'm doing is at least making sense. Like I hope it doesn't seem too complicated. All I took was a bunch of triangles, and then each of those triangles, I just drew these pursuit curves, right? Going back. Uh-oh, I didn't want a full screen. Okay. Let's go back here. Let's see. Yeah, so if you're just joining, all I'm doing essentially is, I'm taking just a bunch of polygons, and then in those polygons, I'm just drawing these curves. How about random turns and not always clockwise? So that's that's also probably a project for another day, though I'm about to say something that might satisfy you. So one thing that I didn't like about this one is that they're all turning, as exactly as you say, clockwise. And the neat thing about this particular drawing is that these cycles, like the face cycles, each have a degree of 2 if you look at them. So for example, there's a hexagon worth of triangles that are all touching each other, right? Which means I should be able to flip half of them. You couldn't do this when we were doing hexagonal tiling. So you couldn't flip like half of them and have it still be aesthetically pleasing. I hope what I'm saying is making sense. So for example, like if you look at all the triangles touching each other, right? So for example, if you draw like this triangle, this triangle, this triangle, this triangle, this triangle, and this triangle, there's 6 triangles touching each other. And they're all going in the same direction, right? They're all going clockwise. And so I didn't do random turns. Actually, I could write random turns if you like. It's actually not that hard. But my idea was to do this and shift half of them to be counterclockwise. So you take all your triangles, right? And you have every other one be counterclockwise instead of clockwise. And there's a lot of Stokes theorem energy here, but the idea is it'll give you a consistent orientation on the plane, right? So if you turn like, so that was my idea, which I guess is similar to your idea, Petrus. I hope you find it satisfying. So, and then this one would be the other way, and this would be the first way, and this would be the opposite way. So this will at least give you a consistent orientation all around the plane. Now, let me tell you something. This should not have been like a particularly hard thing to do, but unfortunately, it caused me a lot of pain precisely because of the way that I implemented things in my code. So I hope the idea that I had is making sense to you. So like you have a bunch of these things, they're all oriented counterclockwise. I basically want every other of them to be oriented the other way. So let's see here. I think this is more of the same. Yeah, this is more of the same, but just with better framing. Let's see here. So for this one, I had to come up with like a decision for like looking at the triangles, which ones I wanted to flip, because the triangles were not indexed in a way where I could easily decide which ones I wanted to flip versus which ones I did not want to flip. And so the idea was to compute the kind of like centroid of each triangle and then round and then just figure out what its remainder was when you divided it by 3. And that's how I was able to decide which ones I wanted to flip and which ones I wanted to flip back. And after a lot of pain and suffering, that did work. And you can see it here. Okay, and honestly, that's kind of cool. So this is what happens. So I hope that satisfies you, Petrus. So this is what happens when you rotate half of them the other way. Honestly, I think that's kind of a beautiful tiling. And one other thing that's very neat about this is that I do believe, and correct me if I'm wrong, but I do believe all of these triangles are similar, except for the one in the dead center. I guess that one isn't similar, but here I can like artificially get rid of that. There you go. Now it doesn't exist anymore. And so now you have a tiling where kind of all of the triangles are similar to each other. Honestly, that looks kind of cool. I like it. I showed it to someone and they said it had a little bit of a bathroom wallpaper energy to it, which I don't disagree with. I feel like you could see this in the 60s in someone's bathroom or something like that. But Petrus also mentioned random rotations. We could try it. So just here, I have a very complicated decision system. It's really not complicated. It was just, I don't know why. I had to stare at this for like an hour and it just never ever worked, which is, I guess, something that just happens when you program. How about instead of this if, I'm just gonna delete this if. Okay, so we're trying random rotations now. Instead, we'll just generate a random real. And if it's less than a half, so random real will generate a real number, I believe, between 0 and 1. And so if it's less than a half, it'll reverse. Let's see. Okay. Wow, that's kind of cool, actually. Petrus, good idea. So in this one, they are randomly rotated. It's kind of cool. I do like that. It kind of makes me want to go back and rotate my hexagons randomly and just see what happens. So, oh god, yeah, I'm probably gonna break everything as I do this, but I guess that's part of the fun. So, I'm just gonna copy this code and put it up in hexagon land, and this could break everything, just so you know. But yeah, it is surprisingly non-random, isn't it? All right, I don't know what's gonna happen. Literally nothing. I don't think it worked. It should have flipped some of them, but it didn't flip any of them. Okay, I would have to stare at this for a while to figure out. As you can see, this is very, I was awake last night writing code. There's like not a single comment. And yeah, everything is just horrible. So I'm not sure if I will be able to, well, you know what? I'm still going to try it. So I'm going to try it. I kind of want to see what randomly rotating hexagons are going to look like. So I think what I want here, I'm sorry, this is not going to be useful to any of you. This is me being an idiot on stream, but okay, so I'm just gonna cut this out and have that be my set of points. Okay. And then V will be my mesh of the points P. Okay. Let's see here. Okay. And then I need to, and this is all like Mathematica nonsense, but I'm just going to copy this, and then it might work. Okay, I'm getting ready to, uh-oh. I think Mathematica froze. And also my stream might freeze. Yeah, it froze. Oh, no. Oh, no. Okay. I'm going to close the program. Let's just hope that I saved recently. Okay, see, that's why you don't code live. All right. So, you know, I did save not too long ago, so. But I did love that random thing. So Petra says maybe you should fill more of the hexagon. Sure, I can fill more of the hexagon. Do you mean with a random rotation or without random rotation? Yeah, filling more of the hexagon is not hard. So you just, there you go. That's more of the hexagon filled. Is that what you wanted, Petros? I mean, that does look kind of cool. I did definitely try this on my own as well. So that's kind of neat. Also, a really dumb thing to do is to experiment with colors, right? So you can try, of course, filling things with random colors. So, ooh, that's kind of cool. So I'm going to do black edges. Yeah. Well, I actually don't think, so I don't think the issue was that more was filled. Like, even if you filled a lot less of this, you would still see that the orientation was different. All right, Ken Haley says ick. So, I mean, you know, it's something. Maybe we could go for a checkerboard pattern. That could be fun. Let's see here. Okay, it's not going to be a perfect checkerboard pattern. It's going to be like a half-baked checkerboard pattern because of the way that I've done things, I'd have to put in significantly more effort to make it a real checkerboard pattern. But let's try it. Let's try it. Let's do black and white. Let's go black. Let's see. White. Black. I think I wanted the outer one to be white. That's kind of cool. It has a very Batman villain energy to it. Though, like I said, it's not a real checkerboard pattern, unfortunately, because of the way I've done things. So all of the external ones are going to be white. I don't know if I could. I mean, I can change it, but I don't know if I don't know if I could successfully think through how to change it while I'm live. You know, maybe I could. So I think I could get a true checkerboard. I'm just going to try something, and if Mathematica crashes again, I'm very sorry. So let's see here. We could. So my idea is I already have code that alternates half of them. What was the artist I was talking about? Charles Perry was the person's name. And he's the person that made the icososphere. A gradient would be interesting. Okay, let's try a gradient. I was gonna try and get a true checkerboard pattern. So what do I mean by true checkerboard pattern? I don't like the fact that these neighbors are all white. I would have to put in like 5 or 10 minutes of effort to figure out how to get it to truly alternate. But since I have an actual request from chat, I will honor it. So let me do that. So let me look up what color gradients exist in Mathematica, and I'll add a gradient. So let's see. Let's see, color function, color rules. Okay. This isn't too hard. I think this should only take me a couple minutes to do. So I forgot the command. If anyone knows what it is, let me know. But let's see. Oh, I know how to look it up. Actually, I don't know why I'm not showing you what I'm doing. It actually makes things less interesting. So I'm just looking up how to generate random colors in the documentation. And okay, yeah, there it is. You can go to color data, and if you give it a random number between 0 and 1, it'll generate a random color. So the command I need is color data for a gradient. And so I just need to look up the gradients that exist in Mathematica. So color data. So color data gives a color data function object. Okay, that's good. So but what are the gradients? No. If you type in gradient, of course, it's going to try to compute the gradient of a multivariate function. Let's see, though. Scope. Yeah, see how it has, like, watermelon colors? I want a list of all of those names. That would be what I wanted. Would it be here? Okay, wait, hold on. Oh, color scheme. That's what I need to look up. Okay, it takes me back to the same place. So what is the list of color schemes in Mathematica? Okay, these are more, it's showing me more schemes, but I just want like a list of all the color schemes with their names so we could pick one. I don't want to waste everyone's time while I figure this out. But for example, this is a color scheme, right? Southwest colors. Let's just try it and see what happens. So, yeah, let's try it. So, what I'm gonna do is, for the first polygon, I'm gonna do color data. What was it? Southwest colors. Okay, hopefully that's like an existing color schemes. Evaluated at 0. Let me just make sure that that works. Yeah, that works. So okay, so now I want a gradient going inward. So what I'm gonna do is, instead of this, I'm gonna sew at color data. Here's it. Choose color scheme. Oh, wow. Okay. You can just do this. This is a list of them all. Okay, that's what I was looking for. Ooh, mint colors. I'm sorry if everyone hates my my taste in colors. Let's see here. Oh, is the stream frozen again? No, it's showing up for me. So I don't know. Let's see. Let's try mint colors and do iterations over max iterations. Polygon at current array. Okay, should have done, now I have inconsistent color schemes, so hold on one second. So was it mint colors was my color scheme? Okay, well, that was a significant amount of effort, but I hope you can see. Okay, now we have a gradient. That's cool. So let's see. I don't know what other... We could try a different gradient. Actually, let me get rid of the edges. Oh, wow. That looks kind of cool. If you get rid of all the edges. Has like a neat effect to it. Though I feel like it would look even more beautiful if I picked a better color scheme. How about rainbow? Okay, should probably rainbow. Okay. Okay, ooh, I like that one. That's kind of cool. Yeah, I kind of like it too. Okay, so this is once again, I don't like how the boundaries are always the same color, but you know, I don't know if I want to take the 10 to 15 minutes to fix that on stream necessarily. But anyways, I hope that satisfies all of your requests. You know. So yeah, there you go. Yeah, that looks kind of cool. I like it. Actually, you know what else we could do? We could lower the step size. Although my computer might crash again. Let's see. Oh, that's very interesting. Okay, let's try it a little bit and increase the number of steps. Let's do 50. Okay, that's very similar, but by increasing the step size, you can kind of like smooth out the image a little bit more, which is kind of nice. Okay, I've said enough. I want to talk about how I made the actual thumbnail, which, as you can see, is only a couple lines of code. If you do, all you need to do is write something that will make these, right? Given a set of points, it will actually give you a pursuit curve. And then you also need to have something or write something that gives you a Voronoi tessellation, okay? But once you have it, you know, you can start with an image. I just found this random picture of like a blue eye on Google Images, and I pasted it into the document. And then you can ask your image editing software to do an edge detection, or you can do it in Photoshop. Any way is fine. So I just did an edge detection. And then based on the edges that you detect, you can do just a Voronoi tessellation, but just do it over and over again. You'll notice the quality of your tessellation will improve with each iteration. So let me just show you what I mean. This was the computer's first attempted tessellation of the eye based on edge detection. And so all you need to do is just take this and just do the Voronoi algorithm again a second time. And you'll notice that every time you do it, it'll get a little bit closer and closer to a smooth answer to what you're looking for. So see, that got a little bit better. That got a little bit better. And so this is the final one that I stuck with. By the way, if any of you have any image ideas, I'm more than happy to try them out, because literally all I have to do at this point is to just paste a different image up here and it'll take care of the rest of the work. As long as the image isn't too large, it shouldn't be a problem whatsoever. I mean, we can also, but I hope the algorithm is sufficiently clear. You just do repeated applications of the Voronoi tessellation algorithm, and it has like a kind of an averaging effect where you get a smoother and smoother one in every iteration. And so this last one is the one that I, of course, went with because it looks the best. Okay. This first one looks like trash and would have given me trash, results at the end of the day. But regardless, we can try it with like a different image. So let's see here. I mean, we could also, there's so much we could do. So we could, for example, have the things go deeper, though we're at risk of crash again. So okay, so that's the same. What is the input in the? So it's the polygons of the previous mesh. Okay, does that make sense? I hope that answers your question, Andres. So it's just look at the Actually, I'm sorry. Look at the polygons of the previous mesh. Compute their average, like compute their centroid, and then use those points as an input for the next time. And then you'll get another set of polygons, and then take all those polygons, compute their centroids, and then put them in as the input for the next time. Does that answer your question, Andres? Let me know. So as you can see, it's fairly simple. And so this is this is getting very trippy. Okay, at the risk of crashing again, I'm just gonna try it with 30. Yeah. Okay, wow, that's kind of neat. I do have a couple more minutes if anyone has any image suggestions to throw in this while I have it up. I'm gonna go push it back to 10 because this is using up a lot of RAM. Man, I checked my RAM usage while I was doing this, and I was at like 6 gigabytes of RAM just for Mathematica, which is insane to think about. In any case, yeah. So yeah, we can try it. Oh, by the way, each of these polygons is colored with the mean color from the image. So just like take the average of the colors appearing in that polygon in the image, and that's how the inside of each one. All right, thank you so much for coming by, Ken. See you next time. So there's that. I don't know, we could try, let's see. I do have other images here. I mean, I could try the image of the cat that I used. It's my cat. Let's see. So let me just take that, copy, put that in instead. See how it goes. Ooh, I hope the image wasn't too high resolution. Oh, wow, look at him. Look at my boy. Actually, he looks kind of creepy. Not gonna lie. Interesting, though. Maybe maybe this makes for a better thumbnail. I don't know. It's definitely a look. Yeah, that's right. Hello, Emily. But yeah, I don't know. It looks kind of cool. Anyways, that's all I have today. I hope you guys enjoyed it. I hope you guys had a good time doing random weird artwork with me with Voronoi tessellations and pursuit curves. And I will be streaming again on Saturday at 1 p.m. Please let me know if you experiment with these ideas and produce anything interesting. Please let me know. I would absolutely love to see it. And other than that, I hope you guys have a wonderful week, and I will see you next time. All right. Bye-bye, John.